All right, this will be saying what is the effect of a magnetic field on magnetic dipoles, which is to exert a torque. All right, consider this loop of wire in a uniform magnetic field. If we run current through the wire, each segment feels a force as shown. In other words, going this way, we get a force pulling this way. This way, we get a force pulling perpendicular to the field as always, which is this way, and so on. These two basically pull everywhere along the same way, and they cancel out. But these two are pulling offset from each other. They are the same strength, so the thing does not move, but it does tend to spin. This is actually true for any magnetic dipole, whether from a current or a permanent magnet or whatever. A uniform magnetic field will spin it, but not accelerate it linearly. A compass, for instance, turns to follow the Earth's field, but it's not attracted towards the Earth. Compasses aren't pulled down any more than their weight, and they're not pulled up in the southern hemisphere. This illustrates a bit more clearly why there's a torque. The forces are offset. This is the center of mass or whatever, and so it's going to be pulled this way, and this will tend to spin the object this way, and this will tend to spin the object this way, but those are the same kinds of spins. Notice they're each about half a length from the center, which is the point at which it's going to rotate. And we'll define theta as the difference between the angle between the magnetic field and a vector which is perpendicular through the center, the axis around which the loop has been built. Calculating torque and seeing how it impacts motion is a topic from AP Physics 1. It's not specifically a topic in AP Physics 2, although we'll cover some of the results and the important bits. The total torque is the torque from each part, the top and the bottom. And a torque in general is going to be a distance times a force, but only the force that lies perpendicular. So we get a half L times the force on the top times sine theta, and the same on the bottom. And when you round all that out, you get IL squared B sine theta. Don't worry that much about this. Don't even worry if it comes out too much. But the most important thing is that we notice that L squared turns out to be the area of our current loop. And so we end up with that the torque is the current times the area, all times the field times the sine of the angle between them. We define something called the magnetic moment, which we symbolize by the letter mu because physicists apparently don't have enough uses for mu, so we keep coming up with more. So we say mu is I times the area. All right. You'll often have people call this just the magnetic moment, or it's more formally the magnetic dipole moment. But they drop the dipole part because it's redundant, except in kind of esoteric applications. There are such things as magnetic quadrupole or octopole moments, but we're not going to talk about them. And in fact, most people don't talk about them. They're very, well, esoteric. We'll be able to define magnetic moments for things that aren't current loops. So things like a permanent magnet will have a magnetic moment as well, or things like atomic particles. They'll always be in units of amps times meters squared. And ultimately, we'll represent the loops or magnets or whatever we're talking about as vectors representing a magnetic moment where the direction of the vector is the sense given there, that there's a direction the thing wants to orient. Just to illustrate it, when we have a current like this, it generates a magnetic field out, and we'll take that as our magnetic moment, just like a permanent magnet has a moment which is from south to north. So to remind you, the torque is the magnetic moment times the magnetic field times sine of theta. The twisting force depends on three things. How strong the field is, that makes sense. A stronger field makes it stronger. How strong the magnet is, because this is a measure basically of its magnetic susceptibility. How does it react to fields? And then how closely they're aligned, which is measured by sine of theta. The twist is maximized when the two are perpendicular, but there's no twist if the two are aligned. So if we start off with a maximally misaligned thing where the magnetic moment is perpendicular to the B field, then it's going to feel a torque, which is going to try and line this up with the B field. And so it's going to spin. As it spins, it's less and less torqued, and when it lines up, it will no longer be torqued. Now, if there are no drag forces, of course, what would happen is it would spin past that, it would flip, and then it will keep going back, oscillating back and forth, because at this point there's no torque, but there's still inertia that would carry it forward. All right, assume that we hold current loop 1 in place. Would loop 2 rotate? Well, the magnetic moment for loop 2 we can take the right-hand rule, and we see that it is like, oops, has a torque like this. We also know that loop 1 is creating a magnetic field that is going around like this, means that's going out and up like this. So there's a magnetic field which is sort of threading like this. And so we can see that the fields are not aligned, and so it will in fact spin. Oh, it's funny. You can see that I misread how they meant this. They meant going like this. Going like this, this is the correct moment, like that, and it would spin this way. All right, we can see the dipole and magnetic field will be in equilibrium, i.e. not torqued, when they're aligned, where theta equals 0. But will also be in equilibrium when they are anti-aligned, that is, theta equals 180, since the sine of 180 degrees is also 0. In that case, the dipole will not rotate, but it's unstable. Any deviation will cause it to then flip over and go the other way. They set up this analogy in your textbook, which is kind of cute, of if we have a pendulum type thing balanced upwards. So you take something like, let's take a stick, and you hold it exactly vertically but at its pivot at the bottom, it would in principle stay balanced, but as soon as it becomes a little unbalanced, gravity torques it and spins it around. And likewise, if we have the magnetic north opposing the field, then it will stay that way right now. It feels no torque, but if I dislodge it even a little bit, it feels a torque that spins it around. The reason it doesn't flip here, of course, is that it doesn't know which way it should flip. Right? It wouldn't. There's nothing to break the symmetry here to tell it that it should flip rightward or leftward. This idea that we have to break the symmetry ends up being really important in fundamental physics. All right. The principle of an electric motor, which is an important way of getting stuff done, works this way. We attach a loop of wire to an axle, making something called an armature. The magnetic field between this permanent magnet creates a torque on the loop, and that would spin the axle. Normally, the loop would just line up with the field and stop, but we use a device called a commutator, and it flips the sense of the current every time the current gets aligned. It's kind of Sisyphean and kind of cruel, but every time it thinks it's lined up, we switch the sense of the current, and now we have flipped the magnetic dipole, which means that it's now in the unstable configuration, and it will rotate the other way. And it will always keep rotating in the same sense, and so we can spin the axle in the same sense, and we can convert electric power into mechanical power. Eventually, we'll talk about electric generators, and they do the same thing, but in reverse. All right. Which way will this loop spin? Well, doing the right-hand rule, we put curl our fingers into the page at the top and whirl around out of the page in the bottom, which means that the magnetic moment points this way. Note that we can find the direction of the magnetic moment by figuring out where the field is in the center of this. If we were to take the right-hand rule and figure out where our fields are, remember the field would look something like this around each of them. So they add in the center and give us the magnetic moment. And now that we have a magnetic moment which is at an angle to the field, we know that it's going to be torqued that way. So we'll rotate counterclockwise.